YouTube, huh? Tā, varu pārbaudīt tagad.
Так.
Tu dabūji internetu, tad kaut ko bija akcesēs. Bet manu ekrānu tu redzi, jā? Iemest arī meetup komentāros. Netīsim meetupā, jā? Tad vēl ietīkošu.
Sēman, sākot teikt.
Viss strādās, jā? Jā. Okay.
All right, everyone. So today our presenter will be Raymond. He'll be presenting his talk that he did on Rails Camp. He's kind of a celebrity now, so yeah, please proceed. And by the way, you can grab snacks and beers maybe after the talk, but those are free unless you want to pay for them. Okay, all right.
Hello, I'm Raymond Smanovskis. I come from far away from Latvia. Latvia, where is Latvia? Well, that was a question that was asked by many Americans 3 years ago during the London Olympic Games, when US beach volleyball team got knocked out by a Latvian team. And then many Americans were wondering and asking on Twitter questions like, where is Latvia? Do they even have beaches? So thought they have just vampires and castles and stuff. Therefore, I wanted to start with a short geography lesson. So at first, according to some movies, vampires are located here. I don't know if you have watched these movies or not. But Latvia is located across the Atlantic Ocean in northeast part of Europe. And according to some other movies, this vampire movement started in Transylvania, but that's in the southern part of Europe, not in Latvia. But we in Latvia have a 500 kilometers long beach, which is 310.686 miles, if you were wondering. So therefore, beware of Latvians when we are playing beach volleyball. Okay, now back to our topic.
Simon, can I give you a piece of advice?
Yep.
I usually say that I am from Moscow. That's it. No more questions. It's so much easier to explain.
Yeah. Okay, next time. What?
No, build.
No.
Okay, let's. So I was okay. Bet vai arī man vajag vienkārši nošērot šo entire screen? Some technical problems. That's Inception. Yeah. We have some technical glitches. Yeah, so we are making some technical. Just a second.
Okay, the online viewers heard this already, so I'll skip that in my introduction and go back to the start of my talk. Back to my talk. Data warehouses and multidimensional data analysis. Imagine we are building a Rails application for tracking product sales to our customers. And we will have several models for that. We have a customers model, and customers are making orders. They have many orders. Then each order is placed on a particular date. And each order contains one or several order items, which have a quantity and price for the particular product that was bought. And products are then classified by product classes. And we then go forward with a standard choice for a database. We will store everything in PostgreSQL database. So this is our database schema with customers, orders, order items, products, and product classes tables. And we are happy Rails developer. Made our beautiful Rails application. But then one day, our CEO asked us and called us to him and asked the question, what were the sales amount in California in last year's first quarter and divided by product families? Okay, so let's try to answer that question. So let's print out our large data model and try to find where we have these columns. So we identify that we have in product ordered items, we have a amount column. So we need to start with this one. And to get the total sales amount, we can make order items sum by amount. Now the next part of the question was in California, so we need to limit which customers we will use. These customers are in a customers table, and we will add the condition that we limit that the customer's country is USA and state is California. Now the next part of the question is in quarter one of the 2014. order date is located in orders table. So therefore, we need to join these orders, and we could make this condition like change it to that order date is from the 1st of January until 31st of March, but we want to stick to the original terms used in a question. Therefore, we will extract from the order date year and extract the quarter, and then make the condition that the year is 2014 and quarter is 1. Okay, and the final part was to buy product families. So product families are in this product classes table. Therefore, we need to join product classes, products and product classes table, and group results by product classes and product family. Okay, finally, we found out the answer to that question. We can present the result to our CEO. Also, we took a look at what the SQL statement was actually generated by this query, and well, we wrote a little bit less Ruby code than SQL, so we could do it directly in SQL, but we are Ruby developers, we like to write Ruby and not SQL, so therefore we are happy with that solution. And we presented it to our CEO. The CEO asked then the next question, and the sales cost as well. Okay, let's look at our query. Unfortunately, in Rails, the sum method on relation doesn't allow to pass several arguments. Therefore, we need to do some trick there that we need to explicitly select product classes, product family, and then sum of sales amount and sales cost. Then just leave the non-empty attributes. Okay, we found the answer and presented to our CEO. And then the next question was, and unique customers count as well. Okay, now we can add also count distinct of customers ID and add to this query, and we'll get the results. But now we are a little bit afraid that CEO or other business users will start to ask these questions all the time, and every 15 minutes we will need to modify this query, and we'll not be able to do anything at all. It would be better that somehow these end users could query these data by themselves. So we tried to sit with a business user and told that how easy it is to write these queries, but unfortunately business users didn't quite understand how to do that. So probably that won't work. As well as we noticed that as our business is doing pretty well, the date volumes are growing, and we made a copy of the production data to our local computer, and we got 6 million rows in order items table. And when we run some query where we didn't limit any customers or time period, so we noticed that this kind of query already takes some 25 seconds, and so it will grow. Not the best performance for some ad hoc queries which need to be done all the time. So we asked some consultants so what to do, and then some consultants came and told us, well, SQL is bad, therefore these things you should probably move to an SQL database or to make some Hadoop clusters and write MapReduce jobs in JavaScript, and you will get the results. But probably not. Probably we still like SQL, and probably we should return to some other classical approach how to solve these problems. And one of the approaches is data warehouses and dimensional data modeling. And so if you're interested about that topic, then there is one classic book is the Data Warehouse Toolkit by Ralph Kimball, which was the first edition was released almost 20 years ago, and which describes how to solve these problems with SQL databases. And the key part is that we start with this dimensional modeling, what it means. So these are the quotes from this book, that objectives of dimensional modeling is to deliver data that's understandable and easy to use by business users, as well as deliver fast query performance. So how do we do that? So to start with this dimensional data modeling, we also need to design our database schemas in a little bit different way. So when we look at the original question, what we had in this case, what were the total sales amounts in California Q1 2014 by product families. So what we notice is that typically in these questions we have some numeric amounts that we want to aggregate and analyze, and these will be called as facts or measures. And we want to analyze these facts or measures by different dimensions, like by customers or region dimension, by time dimension, by product dimension. So in this way, we're discussing these business questions with business users. We identify which are these facts or measures and which are these dimensions that we need to use. And we will design our so-called data warehouse, where we store the data for analytical needs. And we will do this data warehouse design using so-called star schema with fact and dimension tables. So if you look at some larger examples, then typically there will be one table in the middle and then joined with foreign keys to a lot of other tables, and therefore it looks like a star, and therefore they are called star schemas. And in the center we will have these so-called fact tables. We will use the naming convention, this F_ prefix, where we store the foreign keys to corresponding dimensions like customer ID, product ID, time ID, and we store the columns, these numeric columns with the facts and measures that we would like to analyze, like sales quantity, sales amount, sales cost in our case. And then, so they are reference dimension tables. We'll use this D_ prefix for them. For example, customers dimension, which contains all the customer properties that we are interested in. This is pretty the same as we had at the customers table before. But some dimensions will have a little bit different structure. For example, time dimension. The typical approach is that if we want to analyze these facts by dates, and for each date, for each unique date that we have associated with the facts, we create a separate record in a time dimension table where we pre-calculate all the necessary additional attributes. We extract and store the year, quarter, month, day, both as integers, both as string values, which we can represent to users, as well as we could extract the day of the week or some other attributes, whether it's working or non-working day, etc. And then always each fact will be then related to the record in this time dimension. Sometimes we have not just simple star schemas, but we have so-called snowflake schemas, where some dimensions are then referencing some classification or category dimensions, like in our case, products dimension is then referencing product classes. And then, if we have a lot of these additional classification or category tables, then our database scheme starts to look like a unique snowflake, from the term snowflake schema. We will now create corresponding models also in our application. We create these data warehouse models, where we will put them in a separate data warehouse namespace, and we will have a customer dimension, time dimension, product class dimension models, and we have sales fact model, and which reference corresponding tables in our data warehouse schema. And now the first thing is that we need to populate and load the data into our data warehouse schema so that we can use it for analysis purposes. So some dimensions, loading of some dimensions might be pretty straightforward. Like in a customer's case, the simplest approach would be when we want to load the customer dimension, we just truncate all existing data from that table, and we load the data from our transactional system. Like in this case, I will just list all the columns, all the attributes that we want, and then select from the transactional table and insert into our data warehouse schema dimension table. In other cases, like in time dimension case, we would need to identify all the unique dates that appear in our data. Like in this case, we will select from orders table all the distinct order dates. And then for each date, we will pre-calculate the year, quarter, both as integer as well as a name, so which we want to use to present to our users. And then we will insert all. And finally, when we populate the dimension tables, we need to populate also the fact table, and also the simplest approach is to empty existing fact table, and then we populate it as in this case, we select all foreign key values, and then we select these measures either from order items or from orders table, like quantity, amount, and cost. In this case, we see also that we are using the convention that when we transform order date to the integer time ID, we use that we transform it as a 4 year digits, then 2 month digits, 2 date digits. Then it's easier also to understand what time ID corresponds to what particular date. Now, when we have populated our data in data warehouse schema and we return to the original question, we can get the results with the following query. So the difference is that we will always start from the sales fact table and join the necessary dimensions like customers, product classes, and time. We'll always then put the conditions on dimensions table, and we will aggregate the facts from the facts table. So it is not a quite smaller amount of query that we need to write, but at least it is more standardized, and the structure is more standardized where we understand so what goes where. But still, that's not the best way of how to write these queries, and probably we won't teach our end users to write such queries as well. The problem is that we are still limiting us to this two-dimensional data model, and want to put everything in two-dimensional data model where we have tables with columns and rows. But for these analytical queries, much better data model which can describe how we want to analyze this data is a multi-dimensional data model, where we can imagine, and we can try to imagine that we can imagine multi-dimensional data cube with more than 3 dimensions. We'll use the simple 3-dimensional data cube in this case, where we have as many dimensions, and then in the intersection of these dimension values, we have stored these measures. Like in our example case, let's imagine we have sales data cube, we have customers, product, and time dimensions. And then in the intersection for particular customer, a particular time period, for particular product, we have these measures like sales quantity, how many products were bought, which was the sales amount, what was the cost, and what was the number of unique customers that bought that. In addition to having detailed members in each dimension, we can have also hierarchies in these dimensions. For example, in customers dimension, probably we want to make a hierarchy which aggregates customers by geography principle, that we start with a total aggregation of all customers, then we can expand them by countries. We have this country level, then countries could be expanded by states, and then states to individual cities, and then each individual city to corresponding customers, which are all the products in the city. And then when we do some reporting, we can do the reporting at any level of this dimension. So do country reporting or state-based reporting, etc. As well as in time dimension, we can have even several hierarchies. Probably we have the default hierarchy where we have a time dimension with a which could be expanded into years, quarters, month, and then dates. As well as we could have an additional weekly hierarchy where we can have all the same dates but aggregated by weeks, and then aggregated by the corresponding year where these weeks belong. And there are specialized technologies which can deal with this multidimensional data model, and they are typically called OLAP technologies, which is abbreviation from Online Analytical Transactional Processing. Online Analytical Processing, as opposed to OLTP technologies, which is Online Transactional Processing. So these technologies are focused more on how to do these analytical queries and not to handle these detailed small transactions. And one of the most popular open source OLAP engines is Mondrian OLAP engine by Pentaho. And this is a Java-based OLAP engine, and so we as Rubies probably wouldn't be too happy to write Java code and to write database schemas in XML. Therefore, a couple of years ago, I created a Mondrian OLAP JRuby gem, which wraps this Mondrian Java engine and provides much nicer Ruby DSL on top of that. And now, if we what is the first thing what we need to do when starting to use this Mondrian OLAP? That we need to describe our multidimensional data schema and how it maps to the corresponding fact and dimension tables. And in our case, we will describe the sales cube, and we'll describe that it is using facts table f_sales in the warehouse schema. And then we have customers dimension with which is using customers table, customers table, and with corresponding levels. And we provide the names of the columns where each level is storing its corresponding data, as well as we have product dimension and time dimension, where we have described this one hierarchy with year, quarter, month, and day levels. And finally, we describe that we have the sales quantity, sales amount, sales cost measures, where we use aggregator sum and to aggregate the columns in the facts table. And in addition, we'll use customers count measure, where we will use the distinct count aggregator over customer ID foreign key to get the number of unique customers which have bought corresponding products. Now, when we return to the original question, what were the total sales amount in California in Q1 2014 by product families, and using Mondrian OLAP, we can write this query in much nicer way. So where we just use the terms that were present in the original question, and we don't need to create any more additional technical knowledge how it's stored in the database. So we describe our query that we will query from the sales data cube. On the columns, as column heading, we want to put sales amount measure. On rows, we want to take from product dimension, product family level, all the members in that level. And in addition, now we want to add this filtering condition that we want to select just customers from USA, California, and just the data at quarter level at Q1 2014. And Mondrian OLAP Ruby gem provides this query builder syntax, which will finally emit MDX query statement. MDX is a query language which is used by many OLAP technologies, which is a little bit similar to SQL, but not quite. So using some of the same keywords, but with different meanings. So we see that this mapping is quite straightforward, that it's also saying that we want to select sales amounts on columns, product family members on rows from sales queue, and where we specify this limiting filter condition. And as a result, we get a two-dimensional results object, which we can query, where what we get on column headings, row headings, what dimension numbers, and what are the values, what we get out of that. There are several additional benefits when using this Mondrian OLAP technology. The first one is results caching. So when we will make the first query on the same data amount that I was discussing previously, where we have about 6 million rows in facts table, then initial query where we calculate the total for sales amount, sales cost, and unique customers count over product families, but without any limiting factors, so it takes similar amount of time, 21 seconds. But when we execute the same query after that, so result comes in 10 milliseconds. This is because the Mondrian OLAP does the results caching and does this caching using this multidimensional data cube. So that when we make the query, so it looks at whether we have already these cell values in particular coordinates that were asked by this query. If not, then it will generate SQL statement to populate these data cell values. If we have this result, it will be returned. And the results caching is done on this multidimensional cube level, so it's not done on the statements level. So if we have one statement which populated some measures and do some other statement which needs some additional data, then it will query just the missing data and will populate the data cube. And well, this results cache will be persisted in memory while we don't say that we want to explicitly to clear that. And typically for these analytical queries, we don't need their up to date, up to the second information there. So they're more focused on historical reporting. And so therefore, quite many when using this approach are doing this data load just once per day, or it could be also several times per day. And then when we do the new data load into data warehouse, we can clear the Mondrian cache as well, and then it will be repopulated again with the new queries. But yeah, while it's there, all the repeated queries, especially if there are many users requesting the same information, it will be results will be fetched much faster. When we have defined one schema with some dimensions, we can easily add additional dimensions as well, also using existing attributes. For example, we had a customer's dimension table, which has a gender column with the values F and M for females and males. And we would like to add this as a dimension as well, so that we can analyze product sales by gender. And we can add to our schema definition new gender dimension using the same customers table. We'll use the gender column as key, but as a name expression, we can also provide a SQL expression to translate these F and M values to female and males, which are more understandable to the user. And when we have done that, so we can start to use this dimension in our queries. Queries are known by gender members. We can do even more advanced dynamic attributes-based dimensions as well. For example, in customers table, we have a birth date column, and we would like to analyze sales by customers' age and group their age into several buckets, for example, up to 20 years, 20 to 30 years, 30 to 40, etc. Then we can add a little bit more complex SQL expression, but in this case I'm using also PostgreSQL syntax, that I write this SQL expression that I calculate difference between customer's birth date and current date and compare it with the intervals 20, 30, 40, and 50 years. And when I provide that, so then I will dynamically generate the additional new dimension with age interval, less than 20 years, 20 to 40, 30 years, etc. And use this dimension in our queries as well. And finally, there is also possibility to define additional calculation formulas in our schema. So we have these stored measures like sales amount or sales cost. We can add additional calculated measures like, for example, profit, which is sales amount minus sales cost, as well as margin in percentage, which is profit divided by sales amount. And we can also specify the formatting string to format it as a percentage. And as a result, when using these in our queries in the same way as any stored measure, we get so back the results, and so percentages will be formatted as percentages. And in these calculation formulas, there are also a lot of additional functions that you can use, and basically everything that you can do in Excel, you can probably do it using these MDX calculation formulas. And when we have created these dimensions, measures, and created a simpler query language, it is also possible to provide an easier tool, GUI tool for users how to query the data. And that's what we are doing in EasyBI. So we have built a visual GUI tool where you can drag and drop what you want on columns, what you want on rows, what filtering criteria you want to on pages, but below that the corresponding MDX queries are generated and results are displayed either as a table results, or when we have selected the data we're interested in, we can present the data using different charts as well. And this can free up from the regular performing of these individual ad hoc queries. So let's switch to the different topic. We discussed a lot of three-letter acronyms like SQL and MDX and DWH. So now let's talk about ETL, which stands for extract, transform, load. So we already looked at a very simple ETL process when we populated our data warehouse schema from our transactional data, where we just emptied and loaded the data from there. But in real life, quite often we need different data sources for our data warehouse. We probably can use some data from our transactional database, but then we have some additional data in external CSV files, or accessible with REST API in JSON or XML format. And that this part, the first part is that we are extracting data from different data sources. And then the next step is that we need to transform it, parse different data formats, or unify or standardize the data, identify some unique keys, foreign keys, etc. And finally, load into our data warehouse fact and transaction, fact and dimension tables. There are several Ruby tools for ETL. So one is by Square, like an ETL gem. Then recently there is one new gem, Kiba, which is for row-based ETL process. So this is a sample from Kiba GitHub repository, where you can define some Ruby methods for data transformation And then using the DSL, you can describe what is the source. And the source is a class, which could be a CSV file or some database or some REST API. And then you can describe several transformations which take row as input and then emit row as output. And then you can chain these transformations, which could also be either as Ruby block or also as a Ruby class. And finally, there's a destination, which is a Ruby class, which implements the writing the data somewhere, which could be database, could be also some other CSV file or REST API source, etc. When doing the ETL and when doing processor intensive transformations, like if you need to transform a lot of data, millions of records of data, then Ruby probably is not the fastest language on the world. That might be sometimes slower. But if you still like Ruby, you can use the full power of your computer to do multi-threaded ETL. As quite often we are limiting that we do this ETL processing just in one thread and everything sequentially. And so in that case, I would like to recommend that on the recent GEM concurrent Ruby, which is a collection of several concurrency paradigms that you can use in your Ruby programs. And one is thread pool, different implementations of thread pool, where you can launch a thread pool and then post some work to that thread pool, which will be then evenly distributed between these threads. And then when it's processed, so then it could be passed to the next thread pool. So you can imagine that where you have intensive data processing, then you might make for extraction, make some extraction thread pool, then extracted data pass to the transformation thread pool, and then pass it to the loading thread pool. I made a simple example where we, finally the project used JRuby in this case, as unfortunately in MRI, Ruby, just one Ruby thread will be executed in parallel because there is this unfamous global interpreter lock which prevents actually running several Ruby threads in parallel. If you have CPU intensive code, then you need to use Ruby implementations which use real threads and can run real threads in parallel, so which is, well, I would recommend JRuby as well as Rubinius could be used there, but so JRuby would be probably more proven solution for that, which will use the native Java threads, which use native CPU core threads, and you can use all your CPU power when parallelizing work, what you want to do. So here's a small example looking at the original time dimension population. We had a little bit extracted this insert date method to show that when we selected unique order dates from order table, we then for each sequentially recalculated and inserted these dates into time dimension table. So this is a single threaded implementation of that. So now I tried and made this process multi-threaded. But now I'm using from this concurrent Ruby fixed thread pool class, which will create a thread pool with a specified pool size. So let's create insert date pool as fixed thread pool with a specified pool size by default 4. And now for each selected, we do this select and get unique order dates, and then each order date we push to the thread pool. And within this thread pool, then we insert this date, and insert date is the same method that we had previously. And One additional thing that should be noted if doing multi-threaded work and using active record, you need to explicitly check out active record connections from the active record connection pool. As active record, implicitly when you ask for active record connection, it will look whether for this thread you have already checked out a connection, and it will check out new connections. But if in this case the threads will terminate and active record will not know that, so we will not know that these connections could be checked back into the thread pool. As a result, you might run out of database connections. And therefore, so if you do it in this connection pool with connection block, then it will explicitly ensure that after you do the work, it will be checked back into the active record thread pool. And so we post all this work, and then finally we do the insert date pool shutdown, which means that please send the message that process all the work what you have, and then shut down the work, and then wait until all the existing threads will complete their work. And always benchmark what results you get. And so in this case, I also benchmarked on my local computer that the first time dimension load in single-threaded mode, it was more than 5 seconds. And so I found out that doing in 4 parallel threads, I was able to reduce the time more than 2 times. It was a little bit more than 2 seconds. But also be aware that if you start to increase the parallelization, quite often you might again get back slower results. As in this case, when I started to increase the number of thread pool size, so the time started to increase. And it didn't do the detailed debugging yet, so I assume that now the bottleneck is the Postgres database, where in the same table we want to make very many parallel inserts, and now the Postgres database starts to log that as to perform better when there are less parallel connections. But always do the benchmarking, and if you are using JRuby, then there are already some standard JVM tools like Visual VM or Java Mission Control, which you can use to analyze how loaded your CPU is and whether, where are the bottlenecks. And finally, the final topic is about traditional versus analytical relational databases. As we most often are familiar with these traditional SQL databases, which are optimized for transaction processing, like MySQL, Postgres, Microsoft SQL Server, Oracle, which can deal with large data volumes, but they are optimized for this transaction processing, where we do a lot of small transactions, insert, update, select some small proportion of the data. But they are not performing so well when we do these analytical queries over a large set of values. As we saw that as the number of, when we get already millions of rows, then when we do some aggregated queries over millions of rows, then it starts to get slower. Therefore, there are additional a set of also SQL relational databases, but which are optimized for analytical processing. So some of them are like MonetDB, which was one of the pioneers from open source databases, which implemented that, as well as there are several commercial databases, but which have community editions, which allow you to use these databases for free up to some date volume, or up to some, or limit some features like HP Vertica or InfoBright. So I have played with this HP Vertica, which have pretty big limitation, which if you have the raw data size is up to 1 terabyte, you can use it for free. And so this in quite many use cases, that's enough. And there is also Amazon provides Amazon Redshift database, which is this analytical SQL database in the cloud. So if you are using already Amazon, then you might consider using this Amazon Redshift. And what is the main this magical trick, how they manage to make these analytical queries faster. The traditional databases are typically using row-based storage, which means that if you have a table, and table has a lot of columns, then physically on a disk, each row is stored together in the same file block. So there is one row stored, second row stored, next row stored. Now, which is good when you do individual transaction processing, but if you want to, for example, calculate sum of one column, but over all rows, you basically need to read the whole file in all the database file and to extract this one column value, which is why these operations are quite expensive. But all these analytical databases mostly are using this columnar storage. From the logical perspective, you get the same SQL interface that you have tables with rows, but physically how they are stored, that physically each row is stored, each column is stored together. Like we see in this case that there's one column, and then in the same file location, all these column values are stored. And now the main benefit is that, for example, if you want to do the sum or count of one column, then all the values are stored together, and then you can much quickly applications of that. As well as when you have some foreign keys, they are in these fact tables. There are typically quite a lot of repeating values. This, like in our case, some reference to customer or product, etc. And when you have together a lot of repeating values, you can do much better compression. And therefore, these columnar databases are quite often using also some better compression algorithms, so that in reality on the disk, so these values store in less space. Yeah, so these are pictures from Amazon Redshift documentation, and you can go and read more about that. And now I did also some benchmarking on my local machine, at first using PostgreSQL database, and made a query where I had also this about 6 million rows in facts table, and then covered the sum and count, distant count. And on Postgres, it always executed it in about 18 seconds. Even executing it repeatedly, it always still needed, even it low, it has been already cached in memory, the data, but so it's still need to go and read all the data there. And I did a test on HP Vertica. So I installed it in a virtual machine on my laptop and didn't do any particular optimization. So the first query executed in about 9 seconds. Well, it's needed to load the data in memory. But all the next queries executed in about 1.5 seconds, which is more than 10 times faster. So it's because of the what I told about this columnar storage, where it can do the sums and distant counts of these columns in a much performant way. And in real life, also probably it won't be some 10 times improvement, but reading some case studies, there are reports that on some real customer data volumes, the speed increase might be 3 to 5 times on the query performance. And so this is very unscientific recommendation, but some general baselines, what you can use in your case, that if the fact table size is less than 1 million rows, then probably you won't get any benefit from using these analytical columnar databases, as typically that the query speed in traditional SQL databases will be good enough. But so as it grows to the 10 millions or 100 millions or more, then, well, the traditional transactional databases will get slower when doing these large aggregation queries, but columnar databases will do okay, or with some tuning, so can be used also for hundreds of millions of rows.
Do you know if like using this analytical type of database for less data, if it's slower?
Yeah, so the main drawback is that individual transactions are much slower on these tables, because then when you need to update one individual row, so it needs to update in a lot of different places on a disk space. So therefore, you should never use it for transactional data processing. And also you need to plan when you populate data warehouse using analytical database, you need to do bulk upload. So typically there are some copy statements that would maybe export some table to some CSV file or whatever, and then upload it, or create a database link and then do the bulk upload. Okay, take this bulk amount of data and then upload it. And then well, when it's a very small amount of less than 1 million rows, so it might be different. Some queries might run faster or on one or other. So the main benefits you can start to experience when you have many tens or hundreds of millions of rows when these analytical databases are typically used. And so that's the way how you can speed up these initial aggregated queries, where even when we have a clear results cache, empty results cache, how you can still make these initial queries perform faster, or how you can then update your data warehouse more frequently and do not need to worry that after clearing some results cache, the initial queries will take several minutes to execute. So, what did we cover? Problems with analytical queries, dimensional modeling, star schemas, Mondrian, OLAP, and MDX, ETL, and analytical columnar databases. And thank you for your attention. And if there are any questions, I'm happy to answer.
First, a round of applause. I had a few questions, but you answered them. So, essentially, the idea behind this data analysis is that you do bulk import all the time, even with the relational databases, right?
With the relational databases, so how we are doing, this is one typical approach with the relational databases, that you do the first load as bulk upload, but then you can do also incremental data loads. So you can store maybe what was the timestamp until which you have processed the data, and then you can just query the data which are updated or deleted or updated or created after that. Well, the typical problem is that if in the data source some data might be deleted, then quite often this is not tracked. And then you probably just need to scan all the existing data to find out whether some data are deleted or not deleted. So if you do, then this is this incremental data load, and then you basically need to track, so by some ID value or by some timestamp value, you can track what data you have processed, and then after that, how you do get all the creations, updates, and deletions of the data.
So maybe you have some experience with dimensions that are become obsolete because some time ago some user decided they want this dimension. After some time they don't need it anymore, and nobody even knows that for what particular reason it was created in the first place. So then it's some sort of garbage. It's generally.
So the typical approach might be that if you have some common storage of all the reports, all the queries which are using it, then you might find it out. If you don't, then probably the first approach would be that so if you have this dimensional layer where you provide what is available to users, what is not, so maybe at first you can hide this dimension but still store in the data warehouse, and then if after some while nobody is complaining, then probably you can clean up your data warehouse as well. So then it's also better to create this layer in between. what you present to users and what's in your data warehouse.
And this dimensions description it's like a plain text. Have you considered something about visualizing this data definitions?
Well, there are tools which do it in visual way. So in our case, this Mondrian All Gem, it's for our needs, for programmers' needs, and we are much more productive with using text files, and we don't need GUI tools which will slow us down. And then also the text files can be version controlled and things like that. And also we quite often, because we use this, why it's also better than XML, because so this is live Ruby code that we typically actually dynamically generate these schemas, where we start with this schema builder, and this is yeah. So that's just a Ruby program which then finally emits them static text, but all these GUI tools are mostly supposed to be used just for static, some customer-specific dimensions where kind of some end users are using that, but this is in our case that's a power tool for programmers.
So, and another one question. You told that data is stored in memory when
it's cached in memory. Yeah. So when using Mondrian OLAP engine, it's cached in memory.
Have you some measurements about what data memory amount is needed for, say, million rows?
Well, it's also well. So typically, it caches the results, so more or less what you get and you would present to the users. So in typical queries, so that's already some aggregations of that. Well, so we have sometimes the problems is when you still need to generate if you have some long dimension of detailed kind of transaction rows, or and then for some calculations you need to load all of them in memory and then go through and perform calculations on that. Then it might become slower. But well, in typical implementation, so we just give some gigabyte or a couple to the Mondrian to cache in memory.
Yeah, Raymond, in your benchmarking, it took 18 seconds to run queries against PostgreSQL, right? Just wondering if it was a query.
Like for example, like this one, or
Yeah. So my question is, if it took 18 seconds to pre-calculate and run the query, or just run the query on pre-calculated.
Well, there's nothing pre-calculated, so it's just SQL query against the SQL table against the Postgres tables. So the main which is causing that, because on this, so this is this large table, this sales facts table, which has 6 million rows, and for example, especially this is taking probably the most of the time.
But the data already is there in the sales table, right?
Yes.
Oh, okay.
So this is just example. So when we have already pre-populated the facts table and using Postgres as a solution for our data warehouse. So I was just illustrating why the same query, and now in Vertica I just replicated exactly the same data, exactly the same tables, and without any additional fine-tuning, and just run the same SQL query.
What was the reason against NoSQL approach?
Yeah, you were quite negative.
It was just a joke. Also for different problems, there are different solutions. So this is what is all of technologies data warehouse. So they are, if your problems fit well to this dimensional modeling approach, where you have these measures that you want to analyze by dimensions, then this fits well this approach. Well, quite often now that Well, so yeah, there's also one SQL, so there are a lot of different ones. So there are quite many these NoSQL solutions are quite often used. Well, if you have enormous amount of data, well, you need to store it, but then typically no end user is maybe using them directly. Then they are maybe a source then to create some relational star schemas out of that. So probably, well, when you are at Google or Twitter or Facebook scale, then you will just want to capture all the data in a raw format. Then you probably use some of NoSQL solutions to store the original data. But then quite often when you want to do some multidimensional analysis, then quite often these so-called data marts are created, which are just then extractions of subset of data. But at their scale, these extractions are probably as well many millions of rows to do analysis. So I just want to tell that most of the companies and most of the projects, so they are not at Google and Facebook and Twitter scale, and so if you can start with this traditional data warehouse and dimensional modeling style, then that probably will be good enough for you. But then you need to just look at what's the solution. So if you have some full text search-based analytical queries, then so that's not the domain of this data warehouse dimensional modeling, where this is the main domain is that you have some numeric measures that you want to analyze by some dimensions with dimension hierarchies.
So this book essentially, does it explain only data warehousing or also this multi-dimensional cube stuff that you...
Well, it explains the whole topic. So it starts with how you identify these dimensions, and then it goes to the implementation details as of how you can implement different styles of these facts and dimensions using SQL databases.
Yeah, I'm just kind of blurry right now, these dimensions and how they work and how they are stored. And I can understand that there's a column database and how it works, but how it is connected.
Well, logically, so there's no difference.
Yeah.
So in terms of if you use this columnar data store, you would also you'll have this start schema or this is this logical data model, but then this physical data model, physical data model where you store data in both cases. So it would be some kind of star or snowflake schema that you have this facts table. And what this Mondrian engine does, it does this mapping that we can now imagine that we have this multidimensional data cube, but then it will, due to this mapping, so it will transform all your multidimensional queries to the corresponding selects on fact and dimension tables. So there are also technologies which use some proprietary data formats. In terms of OLAP technologies, there are so-called these multidimensional OLAPs and then these roll-up. MOLAP are kind of which have their own proprietary data storage where they kind of store what you have in this multidimensional way, and they will then store it in this multidimensional way as well. These roll-up technologies, these are which present this multidimensional data cube in memory, but will persist all the data in relational tables. And this Mondrian is the example of this roll-up technology.
Makes sense. Thank you.
Can you say this multidimensional cube is basically a table? The dimensions are columns, like dimension 1, dimension 2, and the last column is this value.
Well, so that's implementation details. So you could so sometimes, and even especially when you're using these, the problem is so that if you could also store everything in a very large flat table. Where basically instead of have one large flat facts table, but then there will be a lot of duplications. Instead of customer ID, you would need to store country, state, city, full name. And so for each row, and then as one customer might buy a lot of products, And so then these data will be repeated all the time. So your fact table will be very huge. So therefore, it is better to extract that have this customer ID and then just reference whenever this customer buys something, then there will be one row and just with customer ID columns, and all the other customer details are there in the customers table, and there is no duplication of the data in the facts table. But when using columnar databases, so they are much better at storing these repeating values, and therefore you might sometimes these columnar databases are, well, when you populate them, you can populate just one large flat table, and then in terms of physical data storage, so they're very good at compressing repeating values, and then they might work quite well. Traditional database will work worse if you will now embed all these dimension columns in the same fact table, as then the size of the fact table rows will increase significantly.
How can I start with this data warehouse? So imagine I have traditional SQL base. Should I move all data to this data warehouse, or should I tell this data warehouse, here is my database, please make sense of it? And it's
well, sometimes you might, well, if your data model is already quite similar to the star schema, then you might, with some workarounds, maybe use it directly like that, or like in this case, this customers table, we have almost exactly, and these customers products and product classes, so they are in this example are almost identical to the corresponding transactional tables. And then you maybe, so the typical thing is that it will work much faster. So if you extract these dates as separate time dimension, and then, but you can start that if you have already some transaction table, then maybe add to each date additional this time ID, which will be calculated for this date, and then you have this separate time dimension table. Well, if you kind of have this data model where is this one main transactions table with all the facts, then it probably already is kind of similar that we have some transaction table which is referencing a lot of kind of dimensions. But if you have, in this case, we have order, some things located in order, some things are order items, then some additional data might, some warehouse might appear where we track some movements in and out of warehouse, additional transaction table. So if you have a lot of different kind of these transaction tables, then it would be better to calculate and extract them into the data warehouse star schema model, where extracting these facts from different sources.
In other words, you still have your traditional schema and another one for reporting, right?
Yeah, so this is, and then probably you use for operational reporting what's now. Yeah? So there you anyway make optimized SQL queries which will show you your current balances, current inventory levels, etc. But this is so for optimized historical reporting. So you can then create a separate data warehouse schema which you can populate, for example, on a daily basis. And then the other good thing is that you can also, if you have these ad hoc queries, then you can offload this data warehouse to a different database, different server, so that your ad hoc queries are not impacting your online transaction performance, where you can pre-optimize everything. So then this could be separate, and then if you make a lot of complex ad hoc queries, so it won't impact your online transaction performance.
I guess, guys, let's just if you have more questions to Raymond, let's not make him stand there for too long, and we can ask questions after, with beer, and questions are always better with beer, right?
Yeah, so we can make that, and then maybe after short break, I can also shortly maybe recommend what some other sessions from RailsConf and what were the highlights.
Sure.
Okay,